All right, in this video we are going to talk about edge colorings. So an edge coloring of a graph G is an assignment of colors to the edges of G. All right, so uh, we had previously talked about vertex colorings, and the way that the edge coloring definition is set up is slightly different than the vertex coloring. Um, a lot of books will set up the vertex coloring similar to how this edge coloring definition is set up. So an edge coloring is just any assignment of colors to the edges of G. Okay, so there's no conditions other than you assign colors to the edges. And then a proper edge coloring of G is an edge coloring of G with the additional property that no two adjacent edges receive the same color. Okay, so with vertex colorings, it had that additional property. Okay, so it's the definitions from our book are set up slightly different here. And of course, in graph theory, the definitions you've always got to, in any discussion or session, you've got to nail down the definitions that you're using because they will vary a lot. Okay, so here we have a proper edge coloring of this graph. Okay, so we can see if we just go around and check every vertex, right, we can see this edge, right, is adjacent to this edge through this vertex here. You can see they have different colors. Here they have different colors. Around this vertex, all of the edges incident with this vertex have different colors. All of the ones here have different colors, right? And here and here and here. Okay, so you can go through and check, kind of systematically that this is a proper edge coloring. If I have any two adjacent edges, they are not the same color. Okay. All right, so that's a proper edge coloring. All right, so probably you can see right away the proof of this theorem 2.2.1, which says if I have a graph, then the number of colors required for a proper edge coloring of G is greater than or equal to the maximum degree of any vertex of G, right? And that's pretty obvious, right? So let's go back and look at our graph, our coloring example that we had, and the max degree on this graph is going to be 4, right, with this vertex right here. 1, 2, 3, 4. So the degree of this vertex is 4. That means we are going to need at least 4 colors to color the edges, have a proper edge coloring of this graph, right? Because we have 4 edges that are all incident with each other. Okay, and so you're going to need at least 4 here. All right, so you can see that situation here, and in this case 4 is we've colored it with 4. So basically that proves, right, that the edge coloring, a proper edge coloring of here, it can be done with 4, and we know that it's at least 4 as well. Okay, that's going to lead us into our next definition. Okay, so on this one, right, if you have a proper edge coloring with less than the maximum degree number of colors, then 2 of those edges at that vertex of maximum degree are going to have the same color, right? Because you have more edges than you have colors. So that's basically how the proof would go by contradiction. A k-regular graph is a graph that has vertex degree all equal to the number k. Okay, so actually that's not the definition that I was talking about, but we will be talking about this later. So this graph right here, the Peterson graph, is an example of a 3 regular graph. If I check the degree, right, of each vertex, it's 3 at every vertex. So this would be an example of a 3 regular graph. Okay, every vertex has degree 3. The complete graphs, right, k sub n is n minus 1 regular for any n. So every vertex, right, has the same degree in the complete graphs. All right, so this is the definition that I was talking about, the edge chromatic number of a graph. So when we say chromatic number, that means we're talking about vertex colorings. So the edge chromatic number, we're talking about edge colorings. And so the edge chromatic number of a graph G, denoted by chi prime of G, that has nothing to do with the derivative or anything like that. It's just to set it off from the chi of G, the symbol that's used for vertex colorings most of the time. So chi of G is the minimum number of colors required for a proper edge coloring of G. So when we were going back over this graph and this particular edge coloring, what we've proved here is that the edge chromatic number of this graph is 4. Right? We know that it has to be greater than or equal to 4 because we know that the edge chromatic number has to be greater than or equal to the maximum degree. And in this case, the max degree is 4. Right? And then now we've exhibited a 4 coloring, right, of the edges. And so that proves that the edge chromatic number of this graph is equal to 4. Okay. Just like with vertex colorings, we have this theorem that's handy when talking about the edge chromatic numbers of subgraphs, right? If H is a subgraph of G, then the edge chromatic number of H is less than or equal to the edge chromatic number of G, right? And that proof is exactly the same as the proof that when we were talking about vertex colorings, right? If I have an edge coloring of G, right, with the minimum amount of colors, then that coloring is also a proper edge coloring. I should have said proper edge coloring of G, right, with the smallest amount of colors. Then that is also a proper edge coloring of H, right, with that number of colors. And now, so H might have edge chromatic number less than that, but that's fine. We know that that the edge chromatic number of H has to be less than or equal to the minimum number of colors that you can color the edges of G with. Okay, so so that will be handy in some cases when looking at the edge chromatic numbers of graphs. All right, let's take a look at some of the particular classes of graphs that we've looked at. First, the path graphs, about their chromatic number. P0 has no edges, so you don't need any colors, right? P1, you just need one color. P2, you need 2 colors, right? And there's no way that you could do that with one color and get a proper edge coloring. With the others, right, they're all 2 as well, okay, because you could just alternate the colors as you go down the path. And it's pretty obvious, right, you couldn't do it with one color because you'd have 2 edges that are adjacent colored the same color if you did that at any of these vertices that are not end vertices, okay. So all of these are 2. All right, on the cycle graphs, if the length of the cycle is odd, right, then it's going to take 3 colors. You can alternate the colors here, right, but you have to, right, whatever color you pick for the first edge, right, then the next edge is going to have to be a different color. And then you can see here, then this one will have to be a 3rd color because it can't be black, right, because it would be adjacent to these 2 edges would be adjacent with the same color, and it can't be red. So 3 is the minimum number here. All right, with the even lengths, you can just alternate the colors here. Okay, and clearly there's no way you're going to be able to do this with one color again as well. And so that same pattern holds up for all of the cycles here. So the odd length ones have edge chromatic number 3. The even length ones have edge chromatic number 2. All right, with the wheel graphs, right, the wheel W3 has max degree 3, right? And if you look at all of the wheel graphs, then that's true. Whatever that vertex is that's adjacent to all of the other vertices, it has the maximum degree, right? And so the edge chromatic number of these is going to be greater than or equal to the degree of that special vertex that's in there. And then here we are exhibiting colors, right? Edge colorings with exactly that number of colors, and so that proves, right, that each of these has chromatic number equal to the number of spokes, right? Our edge chromatic number equal to the number of spokes in there. All right, and so you can see their colorings here. Around the outside, you can just kind of alternate the colors enough of the previous colors that you used to color with just a few colors on the outside, but you've got to color the edges leading into this vertex. There's just no way to get around that. All right. So that's what the edge chromatic numbers of those graphs look like. So that's pretty straightforward, right? Using that theorem 2.2.1 that says that the edge chromatic number has to be greater than or equal to the max degree, and then just showing a coloring of that. So it's, again, pretty straightforward. With the complete graphs, it is not as straightforward, okay? So I'm going to go ahead and just talk about this theorem, and then I'll prove it in a subsequent video. So let n be a positive integer greater than 1. If n is even, then the edge chromatic number of the complete graph and vertices is n minus 1. And then if n is odd, then the edge chromatic number of k sub n is equal to n. Okay? All right. And so let's take a look at some of those. For k1, right, the complete graph with one vertex, it's 0, right? So that's kind of the edge case here. With k2, it's just 1, right? Here, k3, we've already talked about. That's the cycle, right? Also a cycle, so and it's odd, so therefore its edge chromatic number is 3. All right, and so here we have the complete graph on 4 vertices, and around the edge, right, is a cycle of even length, so we know we can color that with 2 colors. And then with these other diagonal type vertices here, we can't color those either black or red, right, in this particular coloring, because of the fact that each vertex, right, has an edge that's red or that's black going in here. And so we color that a third color. So we have 3 colorings here, right? If we look at the max degree, right, of each one of the vertices, it's 3, right? So the maximum degree is 3, and by theorem 2.2.1, we know that the smallest number, right, the edge chromatic number has to be greater than or equal to 3. So that proves, right, that this has edge chromatic number exactly equal to 3. All right, so that one is pretty straightforward. As you can see, it starts getting more complicated, right, the higher the number of vertices is. And so, like I said, I will break this out into a separate video. Okay. All right. So let's talk about Vizing's theorem. So that's theorem 2.2.2 in our book. And that says that the edge chromatic number of a k regular graph is either k or k plus 1. Okay, so that is we are not going to prove that. It's a complicated one to prove. So we're just going to state that. And notice that makes sense, right, for our complete graphs. If we look at those, they're all regular, right? So K5 is 4 regular, so Vizing's theorem says that that's edge chromatic number is either 4 or 5, and it was 5 indeed, okay? K6, right, is 5 regular, right? And so therefore you can see its edge chromatic number is 5, again, right? That is in line with what Vizing's theorem says, okay? All right, again, we're not going to prove this one at all. Just state it and move along here. All right, the very last thing in this section is about cubic graphs and Snarks. So this, a cubic graph is just another name for a 3 regular graph. So remember this Peterson graph we talked about is 3 regular. So it's a cubic graph. And then a snark is a cubic graph with edge chromatic number 4. All right, and that has been pretty interesting area over in the history of graph theory. So let's take a look at some of the other ones. It's the smallest snark there is. Here's another one that's been drawn out. Here, the flower snark, and you can see there's some other really interesting flower snarks in here as well. Okay. So, and the Peterson graph, right, was the only known one of these for quite a while. And so it's been a pretty interesting area of research in here. So I just want to mention that because it's got some pretty neat looking graphs and pretty neat looking results in this area here. All right, so that's it for this video. Again, we're going to break off the proofs of the complete graphs, but this should be enough for you to get the homework from this section completed.